And let me introduce the last presentation of the morning and welcome Max Turner, who will talk about TCP/IP and ISO OSI layering and why it's essential to IVN. So Max is an automotive network architect at Eternovia, long bio, by the way. With deep expertise in Ethernet and diagnostics, he joined BMW late in 2002, where he initially contributed to most FlexRay, then V2X and DSRC, and starting 2008, he worked on Ethernet introduction in AutoSAR, and participated in the creation of IEEE AVB 1722, Avenue Automotive Profile and ISO 13400 for DWIP. He led the integration of Ethernet as a system bus across BMW vehicle generation. And after a short stay at Jaguar Land Rover since 2019 at Eternovia as a network architect, he remains an active contributor to IEEE, AutoSAR, Avenue, ASA, Open Alliance, and is editor of the IEEE P802.1DG profile. Thank you.
Thank you so much. And I just realized I need to update my bio because I'm no longer the editor of 802.1DG because it's been published. So if you want to grab that document of the IEEE website, feel free to read it. Give me a call if you have questions. There might be questions in that document. We're going to take a bet how often I bump into anything in here. So I want to talk about TCP/IP and the saying sorry comes later. I just want to say TCP/IP has been around since the 1970s. That's almost longer than I've been around. It has a more than 50-year history. The Internet Protocol Suite, or TCP/IP for short, and I do give my excuses to Lou Berger. Janos Farkas is somewhere there in the back, and I had a very funny discussion with Lou in Madrid the other day about some of these terms, how they sort of in the public mean something else than they mean for the technical world, and sometimes they lose their meaning in the technical world, and we're going to get to this. But I'm going to call it TCP/IP anyway for quite a while. Now, some of you might know the stories about the IMPs, the interface message processors in DARPA's ARPANET in the 1970s in order to actually create the start of the internet. The ISO OSI layer model is from the early 80s. 802.3, the Ethernet standards in IEEE are also from around that time zone. And then when I started working on networks, that was actually optical networks, that was around the triple play discussion. When people were talking about getting telephone, cable TV, and internet over the same connectivity into their home. And it took me until 2019, when I moved to the Netherlands, that I actually had fiber to the home. So working on this since the 90s or whatever, and then seeing it happen in my own home about 20 years later, I thought that was quite interesting. If you analyze the classic AutoSAR stack, you'll find it resembles the ISO OSI layer model to a degree that is almost scary. And I would argue it's actually a bad idea, because the ISO OSI layer model is exactly that. It's a model. And when Christoph just said they're using an Ethernet stack that optimizes the performance of the whole thing, the problem is the ISO OSI layer model is a wonderful model, and I think we should follow it in some design perspectives. But if you create a software that is fully layered, you're going to end up exactly with that problem. It's going to be super inefficient, and you don't want to use it. We introduced, and I'm going to almost say sorry for it, we introduced TCP. Specifically TCP into 13400 back in the days when we wrote the 13400 DUIP standard. I would go back and say in pieces, at least the way we did it, and in the pieces, the way that we described it, that might have actually been a mistake. And I'll get back to that later. So I'm going to oversimplify communication in what I'm going to call TCP/IP. And please be aware, when I say TCP/IP, I mean the whole protocol suite. Going to get back to that later. The main point is we have hosts and we have applications. And we want to be able to identify different hosts with different applications, different instances of applications. And I have completely oversimplified access to web service here on this slide, saying I identify a client or a server, and they identify each other through their IP address. And then they need to make sure that they know I want to talk to the web server on that server. I don't want to talk to Telnet. I don't want to talk to some IP. I want to talk to the web server. But on the other side, you might have multiple windows open that actually access all the same web server. You have 3 search windows to Google or whatever open, and you want to make sure you get the answer back. So you need that local UDP port, a TCP port in this case, in order to make sure that you get that communication matched up with each other. And then on the return, if you look down, we actually just exchange those. So when somebody tells you, oh, all communication for HTTP goes to port 80, no, it does not. The responses come from port 80, and they go to the port that you send it to in order to allow you to identify which instance on your side this actually came from. And you will find that model in a lot of cases where you look into some IP. That same model is applied there. Now, for some of these protocols, there is well-known ports. The 8080, the 80 port, there's some others out there, 22, that people know. And that makes communication a little easier if you use protocols that are well-known and you don't want to actually ask the guy, hey, what port are you offering this on? Yeah? It just makes things a little easier. Why is that important? Because that was part of the argument that we made when we introduced Ethernet into the vehicle back in 2008. And I see the guy sitting there who did it, most of it at least. This is a slide that I literally copied from a presentation that was left over somewhere on a drive from an old BMW presentation trying to compare TCP/IP, and now I'm talking UDP, TCP, and all the other protocols, comparing it to CAN. And the big difference is the addressing, the possibilities of addressing, and what I'm gonna basically call the sort of the expressiveness of the protocol. And I believe in this expressiveness of the protocol. This is where the TCP/IP stack and also the ISO OSI layer model, this is where it is important. Have the expressiveness, have the elements in there that tell you exactly what you're identifying and what this communication is talking about. Whether you look at it that way in your software stack, or whether you take the whole header and look at it in one step, or how you process that, keep that separate, please. We're talking about a model, and we're talking about how to organize things. I'm not talking how to write your software. But having a single element that identifies the sender, the data content, and the destination just doesn't seem like a very smart and a very layered architecture. Yeah? So let's keep those apart. And this is kind of my argument. This does not mean you cannot have sort of quote-unquote data-centric communication by subscribing to data services. But you want to know where does that data come from and who requested that data in order to actually deliver it to the right software component on the other end. And this is not something that the CAN people completely ignored, nor did the FlexRay people. If you look into the ISO documents that describe CAN and FlexRay, they are very, very proud that they use the ISO OSI model. So don't get confused that the people that do CAN, that they don't want to do ISO OSI model. They do, or at least they pretend to do. They put a lot of effort to make it look like an ISO OSI layer model stack. It's just freakishly difficult on something like CAN if you only have a single identifier. If you look at CAN-XL, was just mentioned, they actually made an attempt to separate that out. They didn't do that for no reason. They actually learned their lesson. Absolutely. So, and this is going to be a little bit of a slap here on the side. I disagree. I completely disagree. We do not have everything at layer 2. If we say we have everything at layer 2, we're saying we had everything in a CAN ID. We obviously didn't, because otherwise the CAN people wouldn't be looking at the ISO OSI layer and trying to pretend that they could do that. Sorry, Patrice, I absolutely disagree. No, we need more layers in order to have an expressiveness and in order to describe two-way communication. And it's exactly that two-way communication that tells some of this apart. So let's try put this together with the challenges of zonal architecture and the discussions we're having partially around Open Alliance TC18. Whoops, here we go. I have this weird definition of what I call a quote-unquote real zonal controller. It has a single connection to the Ethernet backbone. I've recently seen a few architectures where you have a zonal controller and then it has like 5 or 6 connections. Not a zonal controller to me, I'm sorry. It connects to very simple devices. I think ideally it would connect to stuff that probably itself does not have software. But I do realize, obviously, in an attempt to actually merge from one architecture to the other, you will have devices that are connected to zonal controllers and that will need software updates. It's just not doable otherwise. But what I feel what is important to the zonal controller is it needs to give some abstraction towards the high-performance compute. It should abstract the devices on the other end. And this is where, obviously, the disagreement with TC18 starts, because TC18 does not want abstraction. And now we're down to this point where Kirsten was talking about in her keynote to Open Alliance yesterday. We said that engineers can discuss problems and value different questions differently and find them important or not important. And to me, this expressiveness of the protocol, this ability to abstract a client, to abstract the host, to abstract the port, to abstract an application, to me, that is super valuable. And I don't want to give that up for an argument of saying, oh, but my stack becomes so much more faster if I only have to look at a single identifier. I don't want to give that up for that. I think that price is too high. Now, the question that I asked to Thomas before about power control, I put down we could do power management through a service API. I do get Thomas's point why he doesn't want to do that right now. I would hope take this as sort of the light at the end of the tunnel. We might be able to do that in the future, and I think Albrecht would be very happy with abstracting even power into a service and actually making it a controllable quality of the system. Yeah, I see a thumbs up. Thanks so much. And actually, also, I think our zonal controllers can actually, if they do need to update stuff on the end of the low end, they can actually manage that software update for us partially and actually save us a little bit of dual banking in the whole update process. But doing actually these real zonal controllers, I know I'm mentioning a lot of people here, but Hari is sitting in front of me, is really difficult. I've been part of a team trying to do this at least one OEM, and it's freakingly difficult to actually just put 4 or 6 zonal controllers that connect everything else. They end up with connectors on them of 600 wires or 500 wires, whatever the number is. It's way too high. You need to adapt them if you want to have a scalable vehicle. You're building a new zonal controller for every vehicle variant because you don't want to spend the money to have the connector there for an option that you haven't sold. Now, you can argue the options are going away. If you look at, and I do this like every half a year, every year, I go around and I try to configure a Chinese vehicle somewhere or a Tesla. And then I go to a BMW or a Mercedes-Benz website, and I try to configure a vehicle there. And usually, when I go to the Asian market, I don't get asked what sort of an audio system I want. It doesn't even ask me if I want an audio system. It doesn't even ask me whether I want a navigation system. In most of the European vehicles, I can configure that away. And I think there is people here probably from Ireland, and they know very well why they want to get rid of the navigation system, because they have a phone and the tax on their vehicle depends on the purchasing price. So if the vehicle gets cheaper because they didn't get the navigation, they get a long-term profit. So the real zonal controller is freakishly difficult to do. So what do we do instead? we actually go to an alternative approach. And we've seen from BMW in the beginning of TC18 why they want to get rid of this abstraction layer, because the abstraction layer is usually OEM specific. And this OEM-specific component is exactly what causes them pain. They need to maintain it, they need to code it, they need to make sure that they have the tools to actually configure it. It is exactly that OEM-specific abstraction component that we're trying to get rid of in TC18. Yeah? And I get the pain point. I'm just saying, don't throw out too much. Don't overdo this. The second problem that I see, and I've obviously displayed this in a little bit of a more elaborate manner, I believe if we follow this approach that has been proposed there, we're actually increasing the number of what I call boxes here in the most abstract way. Meaning components that have a housing, that have connectors, that have a PCB inside, and that have some sort of power management inside. And obviously, I show these little fuses and switches. That's exactly what Thomas talked about. We need to be able to control power from these boxes, absolutely. Otherwise, the whole concept falls apart, absolutely. But I think we are actually increasing the number of boxes in here. And we need to make sure that what we do in savings actually justifies putting in these new boxes, the new PCBs, these new power supplies, and all of that. So what are we going to end up with? Some mix of it. And so we need to somehow find a way to deal with a vehicle that is not fully zonal. If I were to design, let's say, a network for a fully zonalized architecture, oh, my life would be so easy. Yeah? It would be so much easier, but we can't do that. We need to have sort of intermediates. We need to allow somebody to put a skateboard underneath and just abstract away the whole drivetrain and make the quote-unquote, make the drivetrain a zone if you want, yeah? Or integrate some steer-by-wire system from some tier 1 that I happen to have bought it from, and I need to abstract that to my vehicle, and I can't go fully zonal. It just doesn't work. So we need to find communication protocols that cater to all of these use cases. Because I believe if we try to specialize communication protocols, I'm going to use this protocol towards my zonal part. I'm going to use this to my ECUs on AutoSAR. I'm going to use this to my ECUs on Linux. We're just going to get stuck in protocol hell. Yeah? We're going to be talking a different protocol to every ECU, and then the whole talk that Christoph just gave over standardization just completely falls apart. Yeah? So what could we do? Obviously, I'm a proponent of some IP. I'm a little biased there. I've been part of developing it, so why would I not like some IP? And I like some IP specifically because it's super expressive. It has all possibilities to give you the information, who is talking to whom, why, when, where, how. It has all of that. It has versioning of the interfaces. It is super expressive. And if you have ever looked at a trace in Wireshark or in some other tools, you are going to be super happy about all of that information. If you're just stuck there with a single identifier, this data is this identifier, and then you start looking up in some database, what the content is, what the serialization is, who it is communicated from, who is communicated to, have fun with it. Yeah? So two-way communication, this is what some IP was made for, and I think it does it very well. Now, I need to mention the UDP port proliferation, what I would call. I've recently looked back at sort of some OEMs' assignment of UDP ports, and the number that they use for some IP is just staggering. There is multiple reasons for that, good reasons. One of the problems is it is not one protocol. It is multiple protocols in one. The same problem is for 1722. 1722 today, and actually we're on the way of publishing the new 1722 document, but if you ask me, it's a conglomerate of 20, 30 protocols. It is not one protocol. It shares a little header. Everything else is completely different. And the problem is 1722 does not have this expressiveness. It absolutely does not. If you read some of the annexes, one of them I've written myself, there is very, very little information given about which parameter depends on which. Can you choose this individually? Is the one parameter only per the other? Sort of these concepts of messages per service. So the same message ID can appear under different service IDs and meet different things. That's a clear concept in some IP. That concept does not exist in 1722. The semantics of the bus ID, I would say, is random. And it's actually, in that case, it's not useful. And then obviously we can develop something new, or we can use something that somebody invented. Proprietary solutions are just proprietary, and I'm not going to talk about them because I probably either have an NDA or I don't know about them. So, with excuses to Lou Berger again, I'm going to talk about the TCP/IP protocol suite. Both UDP and TCP are a part of that. If you want to read up in RFC 1180 what else is contained there, feel free to do. TCP, I said it in the beginning, I think TCP in a car is a bad idea. Carl gave a talk a few years ago about optimizing the TCP arrangement on how to make sure that we get this all arranged. Guys, wrong approach, in my opinion. I think TCP most of the time is the wrong way to go. My problem is there are still one or two problems where I don't quite have the perfect alternative. Yeah? Had discussions about what to use. Doesn't matter, but as long as we stick to the IP and to the port concept, I think that is very good. I hear a lot of times that people can't configure all of these elements. Hey, if you can configure a stream ID, you can configure a UDP port. Copying addresses when you respond, copying port numbers into the changing the source and destination. If you're telling me you can't do that in hardware, in a response, you have to always respond to the same port, come on, don't give me that. Implementing an echo or an ARP request, people have done that in hardware. I've actually been part of a project where this has been done on an Ethernet side channel. It's not difficult. UDP checksum offloading, not difficult. Sending out a predefined service discovery message. Yeah, if you say I need to follow the whole service discovery stack from AutoSAR, yes, that is difficult. That's not what you need. You need way less. Implementing the minimum of a TCP/IP stack in edge nodes is doable, and it has been done before, and I don't think it's a right argument to get rid of it in something like the remote control protocol. So let's talk a little more about strong semantics, and I'm way too slow here. I'm going to run my time, I think. Unique layer 2 MAC addresses are really worth something. First of all, they don't create a lot of work. Instead, they actually fill, for example, your address resolution table from the very beginning. Before you even exchange any application message, your switches will have learned all the paths that are necessary. Unique addresses on layer 2 allow you to exchange, to mix devices in different setups. You can put two devices of the same type in a setup and still be clearly separating them through their MAC addresses. And the reversing of source and destination in a request response is obviously a useful thing in the network topology because it helps your switch to bring the data to the place where it belongs. Something similar goes for the IP addresses. I went back to an old presentation where somebody said ring swaps, where you take a device out of one vehicle into another to check is the device the problem or is the vehicle the problem. So you take one device, put it into another vehicle, you just swap the two devices and see which one now works or doesn't. If one of them didn't work before, you still know which device you have. It gives you a serial number basically in every message. You know exactly where this came from. This can be valuable in error tracing. Service discovery, I think, is a very useful thing to have, especially in something like a hypervisor environment where you have abstraction on top of your Ethernet link. And obviously, reversing, again, source and destination and request-response communication is absolutely worthy. I got to speed up here a little. UDP ports can identify protocols, but they can also identify instances. And what I showed you in the web server example from the very beginning, they actually already do both. And if you look at some IP, they do this maybe a little too much almost. Yeah, we've kind of overdone that. What is nice about this whole concept of having a service approach is the concept of a service contract. Because the service contract now also entails the QoS part, the quality of service part. And what I like about this is actually that if you have this identification that this is a certain service, it is very easy for your switch to apply a certain quality of service to that communication. It can notice that there is a little bit of pre-configuration needed. It's always needed. You always need to pre-configure it. The switch will never automatically know how to handle this. So if you can communicate that very easily, that is actually a nice thing to have. Sessions and sort of this whole discussion of talking to multiple instances is invaluable. We always, in our training on some IP, we always gave this example of this addition service that sent you 1 + 1, 2 + 2, 3 + 3, and you get 462 back. You need to make sure that you know which question was which answer, especially if those questions were sent by 3 different software components. Because otherwise, the software component that asked for 2 + 2 actually gets 2 back, and is going to get very confused. We're going to jump over the rest. Why was 1722 layer 2 based? For DMA. Because at the time, DMA concepts were very simple. We wanted to make sure, and you'll find slides back from those days, where people said, oh, noticing that a DMA packet, or that I need to take a packet and DMA it somewhere, I need a very small identifier to do that, because we were doing it with TCAMs and all sorts of very limited hardware. But actually, if you compare the concepts to something like RoCE v2, remote DMA over converged Ethernet, RoCE v2 runs over IP. That's the v2 part, because there was a v1 part over Ethernet, actually, only. So IP does not keep you from doing DMA. And DMA is important. DMA gets you the problem out of the way of having to have interrupt handling and all of those problems with small messages. If you want to handle a 10 gigabit link on an interrupt basis, I think you're doomed to fail, basically. So in comparison to some IP, if you look at something like 1722 or RoCE, they have a very limited expressiveness of what they can do on the protocol layer. And again, that might in some cases not actually matter where they were designed for. I believe, because I believe in this descriptiveness of the ISO OC layer model, I think this is important. And as long as it doesn't keep us from doing DMA and all the stuff we want to do in the network, I'd rather keep it. And I don't think it does keep us from that. And with that, and being a little late, I'll leave you to read the conclusion later on when you download the slides from the event, or you take a picture of them, and I'll open this up for questions.
Thank you, Max. Any question, or people are hungry? No?
Albrecht Schwarz from ETAS. Let's say at least a comment from a network engineering perspective. So many communication concepts are mixed here together. It's difficult to sort them out again. Yeah. So at least the proposal to use the layering paradigm when engineering communication systems, this is just mandatory. Yeah. And the layering paradigm introduces inherently a service concept. It's a service-oriented mindset in engineering such communication systems. And there's, of course, protocol layering, but the layering paradigm is not only limited on protocol functions. You could also provide a layer on the entire network itself. Software-defined networking, there's a resource layer, a decision layer, application layer, yeah, and so on. So I think this absolutely makes sense, yeah.
And I would obviously agree, and I would add to that, we need to be able, because a lot of those are remote controlled in some way, shape, or form, or they talk to each other, we need to actually express those in the protocol as well, which is where I see something like a some IP service ID, a some IP message ID. This is exactly where I see this additional abstraction of application services beyond the networking services.
Yeah. Then the next paradigm should be considered. This is using network planes, a user plane or data plane, control plane, a management plane, and then the requirement of service discovery could be achieved in different ways. Yeah. So it's difficult to answer on that in general because you need to know the system context and the operational context there. So this is the plane concept. Yeah.
Exactly, and I wanna add on to a comment that I made yesterday in the open discussion, because I think it hinges exactly on this abstraction and this service discovery thing. If you have a single shared medium bus, and there is like, I don't know, 8 or 10 nodes on there, the concept of service discovery is probably completely pointless. Because everybody hears everybody, the bus is busy, there is very little chance of people, quote unquote, misunderstanding or communicating to the wrong partner. But if you look back at this mixed network that we're envisioning for the vehicle to go to, because we didn't have one clear vision. If you look at this and you imagine that guest OS somewhere on the what is it, the right-hand side of the device, and it wants to talk to something on a shared bus down there, if you try to do this quote-unquote signal or data centering, and you just burst out some multicast to somewhere, and everybody in between needs to know where stuff needs to go, this is not manageable. So what I wanted to express yesterday in the question that I had there was, if we have a network like this that is a lot more complex than just a single strand of a shared medium, we need to make sure we have the right abstraction to actually talk to every device and actually abstract that device. Do we still have time?
Of course.
Oh, yeah. Thank you, Max. As usual, I really enjoy your presentation, so congrats. And my question is regarding, how to include the time-aware, let's say, traffic inside your proposal. Thank you.
Yeah, okay. How many hours do I have to answer that? Okay, so the problem that we have also in the TSN discussions is the moment you make any traffic, quote-unquote, time-aware, I would argue you're making your whole network time-aware. Because what most people that tell you, oh, I can deliver a certain service at a certain quality of service, what they're usually not telling you is, oh, by the way, I'm going to be dropping off something else. And when people talk about time-aware networks, basically they're asking you to say, okay, this stuff needs to get there in time, and the rest of the stuff I'll drop for you because you told me the other stuff is more important. My problem in the vehicle context is I actually don't really know what to drop. So that concept that we have in IT and telecommunications, where the assumption is there is a random flow of traffic, and at times traffic is so high that I cannot guarantee your request for time-aware communication, I can drop something else, because that something else is going to fill up the gaps that are going to come in this random communication pattern. My strong belief is, and feel free to contradict me, we don't have that in the vehicle. The vehicle is dominated by cyclic communication. We have a very flat usage curve of the bandwidth that we use because our sensors are active. We have safety-relevant communication, where we need to have keep-alive signals, and where we might send information completely oversampled just to make sure the other side knows that I'm still alive. So the communication pattern of I have random bursts and I drop some of that burst in order to fill up the gaps where I didn't have a burst, I think that doesn't work in the automotive concept. And so if you say you want to make your traffic time aware, I agree, but then the agreement is the whole communication becomes basically time aware. And we need to make sure we understand that the concept of just saying, if this is more important, I drop that, I don't think that's the right approach. Or I would offer a discussion about it. What do you want to drop? Because look at the TCP problem that Carl explained 2 years ago or whatever. ECUs are hardware, hardware costs money, so memory costs money. People don't want a buffer, right? TCP, 1722, all of those protocols, they did rely on buffering. If you look at the presentation time in 1722, all it says, network, get this there as fast as possible, and then the buffer is going to sit there and wait for the presentation time. It is buffer designed because you don't know how large the network is. The network might be small, or you might have some redundant path. And then the two things travel in very different ways, and then you actually have a problem when to buffer, where to buffer. Yeah, I'm going to shut up now.
Thank you. So we have to increase the data rate then.
Actually, increasing the data rate has one upside, or two upsides. It earns me money, and it actually reduces your latency. So the point is, in order to justify my money, you need a good reason to do that. Why do we increase data rate? Increasing data rate just to reduce latency, I think that's a lame idea. So we need a reason to increase increase data rate, and I've given this in other talks. The only thing in our vehicles today that actually generates any amount of data, and if you look at the Toyota presentation from this morning, the only thing that generates a relevant amount of data, and I'm talking a gigabit and above, is cameras and potentially in the future imaging lidars or radars. Everything else in the vehicle, bird feed.
Okay, thank you, Max.
Thanks.
Okay, thank you. Let's stop for now, and maybe I can invite Max staying close to the stage, maybe Thomas as well, Vladislav. Come here. I think Christophe left. So if you have some more questions,
Sure.
Maybe let's stay a little bit close here.
Absolutely.
And for the others, have a nice lunch. Next conference will be 2 p.m. here, and we'll move to the validation topic. Thank you, everyone.
Thanks.